Hello, my name is Quesada Torres and I work as Site Reliability Engineer at Google. In this Tech Talk, I am going to present the Google production environment, or at least a self-consistent way in which Google infrastructure has worked. Some details may have changed over time. I am going to introduce everything needed to develop, deploy, and run a large-scale service. Please note that I based these slides on the SRE book, which I'll link to at the end of the talk. Credits for the contents of this Tech Talk go to the authors and contributors of the book, and especially to J.C. Van Winkle, who authored the Production Environment at Google chapter in it. Let's start by briefly discussing some concepts related to the physical setup of Google infrastructure, that is, network and machines. Google infrastructure relies on three different levels of network. The Edge network connects Google infrastructure with ISPs to get traffic from and send traffic to users. Data centers communicate with each other by means of a globe-spanning backbone network called B4. B4 is a software-defined networking architecture that uses the OpenFlow Open Standard Communications Protocol. The network fabric deployed inside data centers is called Jupyter. Jupyter consists of hundreds of hardware switches that form a virtual switch with tens of thousands of ports and a bisection bandwidth of 1.3 petabits per second. Now, in terms of request handling, most external requests, after they go through the Edge network, hit Google Frontend or GFE. This frontend acts as a reverse proxy that routes the requests and the replies between the users and the processes running the application. The last missing piece is the Global Software Load Balancer, or GSLB, which balances requests at three different levels. It does geographic load balancing for DNS requests, like to www.google.com. It load balances at user service level, for example to YouTube or Google Maps, and it load balances individual remote procedure calls, or RPCs. So a specific user request would go from their local network to their ISP, then to Google's Edge network. Once in Google network, it would hit GFE, and from there the payload would go through GSLB, B4, and Jupyter, potentially with several levels of indirection, until it hits the server. Then the response goes all the way back to the user, all of this in just a few milliseconds. The physical layout of computers within a data center is the following. Google Production Fleet runs on many campuses. Within each campus, there can be one or more data centers. Within each data center, there can be one or more clusters. Within each cluster, there can be several rows. Within each row, there are several racks, and within each rack, there are several machines. As you can imagine, this adds up to too many machines. It is impossible to manage that many machines manually. The teams that maintain concrete services need an easy way to schedule and manage jobs in these machines. There is software that is in charge of managing what runs in each of the machines in a cluster. Let's see how it works. Let's imagine users or teams want to run jobs in a cluster. Those jobs can be indefinitely running servers or batch processes like a MapReduce. Each job can consist of more than one and sometimes thousands of identical tasks. That is for reliability, but also for scalability. A single process may not be enough to process all the traffic. Each job has concrete resource requirements, for example, 3 CPU cores per task or 2 GB of RAM per task. Users launch these jobs by using tools that read config files. Requests arrive to a Borg manager process. The Borg manager checks with a scheduler in which machines the tasks should be scheduled to optimize the bin packing. Then it asks the Borglets running in them to start the tasks. If a task starts malfunctioning, it is restarted, possibly in a different machine. Please note that given that tasks are fluidly scheduled over machines, IPs and port numbers mutate, and it is not possible to rely on them to refer to the tasks. So there is an extra level of indirection, Borg naming service or BNS. A BNS address like this resolves to the current IP address and port of a concrete task. BNS addresses have to be always up to date and consistently stored. Where is the mapping between BNS addresses and IPs and ports stored? Well, the mapping between BNS addresses and IP addresses and ports, as well as logs to elect the new Borg manager if the current one malfunctions, and potentially some other data, are stored in Chubby. Chubby is a log service that provides a file system-like API. It handles logs across data centers and uses the Paxos algorithm for asynchronous consensus. With this, Borg manages a cluster and turns it into some sort of huge distributed computer in which users can run processes. How can users store data in this computer? A first approach would be to directly use the hard disk drives and solid-state drives in the machines where the tasks are running. However, given that tasks are fluidly scheduled, these drives are not a good option for these tasks to store permanent data. Indeed, D, which stands for disk, is a file server that runs on machines in a cluster and uses HDD and SSD to store data temporarily. Colossus is a successor to GFS, the Google file system. It is the layer on top of D that creates a cluster-wide file system that can store data permanently. It offers usual file system semantics and replication and encryption capabilities. Bigtable is a NoSQL database system that works on top of Colossus. It can handle databases that are petabytes in size. I will say this slowly. Bigtable stores maps that are distributed, sorted, persistent, sparse, and multidimensional. Each value stored in the map is an uninterpreted array of bytes. The clients using the table are responsible for serializing and interpreting the data before writing and after reading it from the table. Bigtable also supports eventually consistent cross-cluster replication. Spanner is another storage system that works on top of Colossus. It offers consistency across the world. Plus, there's plenty of other storage options built on top of Bigtable, Colossus, and Spanner. The storage systems complement Borg to turn a cluster into a huge distributed computer that can not only run processes but also store data. But it is more fragile than a personal computer because many machines are more likely to break than a single one. How can this computer guarantee that all the processes are always running fine? It does so by means of monitoring. Monitoring services monitor all the tasks running in a cluster. Borgmon is a white box monitoring approach. Tasks running in a cluster export a set of values that can be gathered using an HTTP request. The Borgmon scraping layer gathers all these values. This layer consists of several tasks that aggregate partial data. It's several tasks for scalability purposes. Then, the cluster-level Borgmon task gathers all the partially aggregate values for a cluster and aggregates them into per-cluster values. This setup is the same in every cluster, and then there's a global layer that gathers aggregate data from all the clusters and aggregates it together. The cluster level and the global Borgmons export the values to a time series database and can trigger alerts. For example, if request error ratio for a concrete service in a cluster or globally is too high. Probers are a black box monitoring approach. They send requests to a task and evaluate the response times and response payload, for example, the HTML contents of an HTTP response. Probers can be set up at the same time behind the load balancer and directly pointing at servers in a data center. This makes it easier to figure out whether traffic is still being properly served when a data center fails, and it makes it easier to detect where a failure has occurred. Let's now discuss how tasks, for example probers in this slide, can communicate with other tasks within and between clusters. Stubby is a remote procedure call mechanism, or RPC mechanism. It is HTTP based and is defined using protocol buffers. Indeed, requests and responses are protocol buffers. Protocol buffers are a language-neutral, platform-neutral, extensible mechanism for serializing structured data. It is like XML, but smaller, faster, and simpler. Protocol buffers take as input the definition of a data structure and generate source code to write and read the structured data to and from a variety of data streams. The open source implementation of protocol buffers supports at least Java, Python, C++, Ruby, and C#, and works across platforms. This is the last piece needed to have a fully functioning production environment for distributed computing. So how do engineers develop, deploy, and run programs in this production environment? Let's first discuss where the code lives. Piper is the repository where the code lives. In 2016, it stored about 1 billion files, 2 billion lines of code, and 9 million unique source files, totaling about 86 terabytes of data and 35 million commits in 18 years. It stores, among others, source code, configuration files, documentation, files copied into release branches, and supporting data files. So let's imagine an engineer wants to do a change to code in the repository. The engineer has to write a change list, namely CL, sticking to Google style guides. It is Google culture to have all code peer-reviewed, so another engineer reviews the CL. Finally, the owner of the modified files or directories is also requested to approve the CL. Please note that in some cases, the owner and the reviewer can be the same person. The engineer triggers the submit, and then per submit checks do automated testing and analysis on the change. If everything is fine, the change is submitted to the repository. How are these projects with code in the repository built, tested, and deployed? Blaze is a build tool that supports building binaries from a range of languages, including C++, Java, Python, Go, and JavaScript. The engineers specify targets, which are the output of a build run, for example, a jar file. For each target, it is possible to specify sources such as files with source code. It is also possible to specify dependencies on other targets and tests. Blaze can also build NPM packages, where NPM stands for Midas Package Manager. These packages are versioned and signed to ensure authenticity. A framework runs continuous testing on the code. The last passing version is periodically picked up by the release tool Rapid, which runs Blaze again to generate NPMs and labels them so that they are identifiable by a name and a version. Finally, Sisyphus does the push to production. Sisyphus is a framework that allows rollouts as complicated as necessary. For example, they can be pushed immediately with canarying stages or to successive clusters over a period of several hours. And that's it. That's everything. Let's now do a quick recap. Let's see how an engineer would use all this technology to develop a service, build it, run it in Google production environment, make it serve external user requests, and keep it up to date. Let's assume that an engineer wants to develop, for example, a high-traffic online forum. They use the development infrastructure to write the code and tests and get them peer-reviewed and submitted, and they build the first project NPMs. They write the configuration files and start the jobs in Borg, the cluster manager. Borg uses Chubby, the log service, to store the mappings from BNS addresses to IP and port of the tasks running the service. External user requests go through Edge, GFE, B4, GSLB, and Jupyter and get to a concrete task running in a cluster in the form of protocol buffers via stubby calls. The tasks use, for example, Spanner to write and read the messages posted in the forum. Borgmon and Provers are constantly running and they fire alerts when request latency or error ratio increase. The server code is continuously tested and regularly built by Rapid and rolled out by Sisyphus so that the tasks pick up the changes to the code and dependencies. This is already a service whose maintenance is practically automated, which engineers can improve and which relies on site reliability engineers to deal with any eventual alerts. That said, let's wrap up. This slide contains a list of open source projects that are alternatives to the different components that I've mentioned during this tech talk. I'll give you a few seconds to skim through the list. Okay. The Site Reliability Engineering book, also known as the SRE book, contains more detailed information on these and other components, as well as some other topics of interest related to production environment, such as reliability and scalability. Feel free to have a look at it in the link listed in the slide. So I hope you enjoyed this Tech Talk. I really enjoyed preparing and recording it. Thank you for watching. Cheers.